عليكم السلام ورحمة الله.
أهلا Khalifa. So today we are going to continue talking about stack and what is a stack memory and how do we deal with stack memory. So basically, if you recall in the beginning of the course, we said that we have 4 different segments. We have the data segment, we have the code segment, and we have the segment, and finally we have the extra segment. And for each of these segments we have a register that is pointing to the top or to the beginning of each of these segments. So our memory is divided into 4 different sections. The first section is the data section, the code section, stack section, and extra section. We call them segments. And in the emulator, also in the emulator, as we showed you earlier, you can see that over here we have the extra segment, data segment, stack segment, and code segment, and data segment. So all of the segments are available over here in our emulator. So what is a stack and why do we need such memory? We already have the data memory. So why do we need the stack segment? Basically, stack is a space used for as temporary storing during the execution of a program. Sometimes you need to store values without giving them names. Usually, if I want value inside memory outside the registers, I will say simply move, let's say 0x35 into a variable called w. Now, w is a variable inside the memory. I can store to that variable immediately, but this operation will require the calculation of the storage location and then moving the data into that location. Instead, we can use the stack. So the purpose of the stack is saving the return. Sometimes when we call a procedure, which procedure is something like a function inside the C++. If you call a procedure, then you need to return, you need a return address. The return address is usually saved inside the stack. Saving the contents of registers used in procedures, passing parameters to procedures, allocating memory for local variable in procedures. So basically, whenever you deal with procedures, you need to deal in a right way with the variables. So you need the stack memory. So how do we deal with the stack memory? So stack works on last in, first out. Last in, first out. So the last data in is the first data out. The last data in is the first data out. The data structure, or sorry, it's last in, first out. So the data is always accessed from top of the stack. Remember, there is only one access point, which is the top of the stack. Insert pushing. So we use the instruction push data to top of the stack. To delete data from the stack, we use pop from for that particular option. So we have push and pop. So this is an empty stack. As you can see, if I push 2, then 2 will be on top of the stack. If I push 9, now 9 is on top of the stack. I cannot get 2 out. If you to get 9 first. If I push 1, then I 1 in. Now if I pop, I will pop 1 first because it's on top of the stack. Remember, last in, first out. The last number to enter the stack is number 1. The first number to exit the stack is number 1. Last in, first out. So pop, I pop 1. The next pop will pop 9. The third pop will pop the 2. It's like the plate stacker. If you ever seen where it's in restaurants, As you put the plates, the first plate entered is the last one to go out of that particular stacker. Now, really, it's basically upside down. Why it's basically upside down? I opened over here to show you. Over here, if I show you the stack, this is the stack. Now, this stack, as you can see, okay, the stack, as you can see, is the pointer is pointing on FFFE, which is the last location. When I push, I will go decrementing instead of incrementing. Yani stack memory, we start from the last location, building backwards. That's why it's basically upside down. So basically the stack is like this. If you push, this is the last location. If you push, this will decrement, and this is the new last location, and so on. So the stack pointer is decremented. Is basically decremented every time. Okay, the stack pointer is decremented every time you move into the stack. Every time you push, you decrement. Every time you pop, you increment. Every time you push, you decrement, and every time you pop, you increment. And the stack pointer always points to the top of the stack. The stack pointer always points to the top of the stack. So if my stack pointer over here, is FFFE, then the stack pointer will point over here. We decrement. So FFFE minus 2, we will be like FFFC, then FFFB, and so on. And when we pop, we increment. So this is how it's operating inside the stack memory. So the stack layout inside the, as you can see over here, this is the extended stack pointer. The stack pointer is pointing over here. This is your free, and this is your current stack pointer. So when we start over here. When we push, we decrement. 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 And now we are pointing over here. So this is your top of the stack. The direction of increasing memory, the addresses, as you can see, and this is the direction of growing stack. As decrease, the stack pointer will decrease. Remember, every time you push, you decrease. So we have the stack segment, not used as a flat memory model. Again, remember the stack segment is not a register, it's a full segment inside your memory. So you cannot use the stack segment as a register. We have the stack pointer, which always points to the top of the stack. The stack pointer is decreased when data is pushed. Remember, we either decrease it by 2 if we are pushing, and we decrement by 4 if we are pushing a double word, and we decrement by basically it's usually by 2 or by 4. Then the stack pointer is increased by 2 when we pop if we are popping a word, and it's increased by 4 if we are popping a double word. So I can show you over here in the code. So over here you can see, let's change this code. Let's say move to AX 0C31231. Okay, then push AX, pop EX. Now this is the first experiment we are going to do. So as you can see here, what's wrong? Wrong parameter. Move AX. Probably no. Okay, sorry. Okay, this should be hexa. Okay, so this is the stack memory. So first of all, I move the value C231 into AX. Then I push AX. When I push AX, you can see that the stack segment is holding C. It pushes a full word, 2 bytes. It pushes a full word, 2 bytes. When now the stack pointer here, where is the stack pointer? Okay, the stack pointer is pointing to FFFC. Okay, this is our stack pointer. It was pointing to FFFE. We decrement by 2 because I pushed AX. And it's always by 2. It's always by 2. Then, if I do pop X, I will move whatever is on top of the stack to BX. Then I will decrement BX by 2. Then I will increment, sorry, BX by 2. So once more, BX will have the value which was in the stack. And the stack pointer is pointing once more to FFFE, which is the top of the stack. See, the memory is still in the stack. Nothing has changed inside the stack. Right. What happens if I try to push AH? Okay. What happens if I try to push AH? See, wrong parameter. Push does not take a byte. Push will always take a word. So you cannot push a byte or pop a byte. You always need to push a word, which is 16 bits. That's why over here you can see that we are holding one word, which is 2 bytes. One word, 2. By the time we move in 2. So we either push a word or push a double word. If we are pushing a word, we decrement by 2. If we are pushing a double word, we decrement by 4. So for example, if I push EBX, okay, if I push EBX, which is 12 FE 6A B3, remember the little Indian. Okay, so first we move, then FE, then E6, FE, then A6, then B3. Now my top of stack is pointing to 814. 814. So what is the process of pushing or popping? So first we decrement. Remember, the stack pointer is pointing to top of stack. So before doing anything to the stack pointer, you need to so first, when we are pushing, remember, first decrement SP, stack pointer, then move data. And remember, the stack will be holding 1 byte at a time. So every time we move. Now we start by the most significant bit. We move it to top, FE, and so on, and then BE. Remember, the Little Indian convention said that the lowest byte is always saved in the lowest address. The lowest byte is always saved in the lowest address. Remember, the lowest byte is always saved in the lowest address. So this is why you are going to save 12 FE 6A, then B3. And when we pop, okay, when we want, so my stack pointer will be pointing to A9. So when we pop, we start by decrementing by 2. Decrementing, sorry, A9, which is 10. So we start the first byte. After that, we decrement. We move 1A, 7B, 39, and 2F. Remember once more, the lowest byte always saved in the lowest address. The lowest byte is always in the lowest address. So in this case, you always need to do it in this way. So when you push, you decrement first, and when you pop, you decrement also first. Basically, this is the other way around. I'm sorry. When you pop, this is my top of stack. See, this is before, because when you pop, you need to increment. When you pop here, you increment. You decrement. So when you pop, we started with 100 and okay, 1000, sorry, and 6. So it contains FE, lowest byte in the lowest address. So first, when popping, first move data, second increment. Compared over here, when we push, first you decrement the stack pointer, then you move the data. Here you increment the stack pointer. Over here, decrement first, then moving. Over here, moving, then increment. Remember, this is the difference. So your top of stack is pointing to FE. Remember, lowest byte is stored in the lowest address. So 2F, then increment by 1, 39, then increment by 1, then 7A, then 7D, sorry. Let me change the color. 7D, then increment by 1, then 1A, increment by 1. So after that, your stack pointer will be pointing to 1008. You need to know how to push and pop and what happens after pushing and popping from the memory. What happens after pushing and popping from the memory, okay? So you need to understand this concept. When I push, I decrement the stack pointer and start saving the data. Remember, the lowest byte is always stored in the lowest. Now, when I pop, I read, then increment, read, then increment, read, then increment, read, then increment. So push and pop instructions are used to access the stack. Push and pop always store and load. Push X, X can be either 32 or 16. So it's either 4 or 2 bytes of memory. Pop can either be 32 also or 16. Now we have also push all double word. When you say push all double word in the Intel 386, basically push all double word will push EAX, EBX, ECX, EDX, EBP, ESI, and EDI. It will push them all into the stack. The reason for doing this, when we are using call and return, we need sometimes to preserve the values of the current registers. When you are calling a sub. So when you call them, you need to preserve the values of registers. So you push everything, and when you want them back, you basically pop everything. Remember, all of these are the registers that we use throughout the working with the programs. Now we can push the flag double word, and we can pop the flag double word. So also we can push the status, which is the flag double word, and we can pop the flag also in the same manner as double word. The reason for pushing the flag and popping the flag, sometimes also you need to preserve after pushing all the data, you need to push sometimes the flag. Now some rules when using the stack. For every push, there must be a corresponding pop. Okay, remember, when you push, you need to pop later on. And remember that pushing will reverse the value. So if I push over back to the program, so let's put in AX value. I can move to BX1122 hexa. Let's make things easy here, and we put 3344 in AX. So push BX. I want to preserve the values. Then I need to pop BX first, then pop AX. So this will basically move 3344 to AX, move 1122 to BX. Now let's check the stack. Move 3344 to the first value of stack, then 1122, which is what was push BX. Now when I pop, the first value I'm going to pop it is 1122. If I want to save it in BX, then I will put it in BX. Remember, last in, first out. The last one to get in was BX. Now, so if I pop, I increment, and now BX will have 1122. If I pop once more, I will have the same values. The same if I do the other way around. This is like exchange instruction. It will swap the contents of the two registers. So I can move, push the two values inside the stack. And when I pop, I will change the values. So because I reverse the values over here, it will change the output of the stack. So you can use you need to be wisely using the stack. Remember what you pushed first and when you need to pop it. So you can access the stack by using the base pointer. We said that the base pointer register is used to access any value inside the stack pointer. Okay, now registers are global variables. In principle, registers can also be used as temporary storage in some procedures. If a procedure needs to use registers as temporary storage, these registers contain useful global information. Their contained information should be preserved. Procedures need to use, procedures are small functions that you call from the main program. When you need them, it's better sometimes to preserve the values of the main registers so that you don't lose the information. So push, pop, call, and return all modify the stack pointer. The base pointer I was talking about just now, the base pointer is often used to access variables in the stack. So for example, access the third word on top of the stack, we base pointer, we move the stack pointer into base pointer, we add 8 to the base pointer, and then we move whatever is over there. So if I go back to my program over here, okay, so let's say after pushing all of this, I can simply say move to base pointer, stack pointer, and stack pointer will be pointing to that value. Then I can say sub base pointer comma 2, then move to dx whatever the stack pointer is, the base pointer is pointing to. So if we go through this program, that will show you. So the two values, okay. Now the stack pointer is pointing to FF. Sorry, I need to push once more. The stack pointer is pointing to FFA. Okay, the stack pointer is pointing to FFA. Now I want to move whatever is in the stack pointer into the base pointer. So the base pointer is also having the same value as the stack pointer. I want to access the memory. So let's say I want to access the first value I pushed in. So I have to do is to increment the values by 2. And this is, sorry, decrement by 2 because the stack pointer is pointing to FFA. And this is done by sub by 2. So if I sub by 2, you can see that the base pointer is pointing to, base pointer F8. I actually need to add by 2. Okay, so we actually need to add by 2 because FF8 will take us down. this is like pushing. I want to pop, so I will just here add 2. And once more, here is the stack. So the stack pointer is pointing to FFFA. The base pointer will be pointing to also FFFA. If I add 2 to FFFA, it will be FFFC. And this value will be now the base pointer. You can see after I add 2, it will be FFFC. And I will move whatever is in the memory location into DX. So now DX is having 3344, which is this value, this memory location. So this is one way to access the stack memory without changing the base pointer, without changing the stack pointer of the memory. Okay, so this is for the stack pointer and base pointer. Now, this is basically what we need to know about the stack. What I want to do is let's take a few examples. So first example, I will say move to AL 44A hexa, and then move to CL3, and then shift left CL. Now shift left AL CL means I need to shift AL with the values in CL. So the first thing that you need to do when you want to shift right or shift left basically is to convert this number into a binary number. So 4A is basically 0, 1, 0, 0. A is 1, 0, 0, sorry, 1, 0, 1, 0. Then you want to shift left means move the bits to the left. I need to move the bits to the left by 3. So these 3 bits will go out and 3 zeros will go in. So the final number is 0, 0, 0, 0, 1, 0, 1, 0, which is 50. Okay, which is 50 hexa. If I want to do the same, but it was shift right. Okay, I want to do the same, but it was a shift right. Same idea. I will say 0, 1, 0, 1, 0, 0, 1, 0, and then I need to shift the bits to the right. So I will add 3 zeros from here, and these 3 are going to go out. So you will have 1, 0, 0, 1, 0, 0, 0, which is 09 as your answer. So this is for shift right and shift left. These are some examples to what we did in the previous class. So shift left and shift right. Shift left, double precision, shift right. Yes?
Why you add 3 zeros?
Because, okay. See here, sorry. My instruction says shift AL by the values of CL. CL contains 3.
Okay.
Okay. I say only shift left AL. I can do also the same over here. I can show you on the program. We can the AL 4A. Okay. So move to AL 4 A hexa, move to CL3, shift left AL CL. So this is the program. So we move 4A to AL, then when we move 3 to CL, then we shift left AL 3 times. When you shift it, you get the answer as 50 over here, which is the answer that we got from the program. But I just want to show you how we got this number. The same applies for shift right. Now, the other instructions, such as shift arithmetic left and shift arithmetic left is similar to shift left. Shift arithmetic left is similar to shift left. Let's go back to the whiteboard. So once more, if I say move to AL, let's say 50B hexa, shift arithmetic left لل AL be 3 times. I can do it like this also. I can either put in CL. Can I? Can see. Yes, it will work. Okay. So I will say shift arithmetic left by AL. Now, first of all, what is the difference between shift arithmetic left and shift left? First of all, B is 1101, 5 is 1010. Shift left, I need to shift the bits to the left. Shifting the bits to the left will first move the bits here. I will add 3 zeros and I will take out 3 values out. طيب, what about shift arithmetic right? If I say shift arithmetic right, now remember shift arithmetic left is the same as shift left. ما في تغيير. Same. Okay, both of them are the same. Shift arithmetic right, AL by 3 times. I will assume that nothing has changed here, so I still have the same values. So AL will be 5, which is 0101, and B, which is 1011. And I want to shift arithmetic. Shift arithmetic means preserve the sign. Preserving the sign when shifting right means if this bit is 0, we keep entering zeros. So, meaning I will enter 3 zeros into over here, and these 3 will go out. So I will have 1 1 0 1 0 0 0 0. These are the new 3 zeros. These are the 3 new zeros. So my answer will be B, and something is wrong. No, these 3 out. Yeah, B0. Okay. Now, assuming that my AL, assuming that I moved to AL B5 hexa, and as I moved this value, I said then shift arithmetic right AL by 3. First of all, we need to change this value into binary, so it will be 1010, and B is 1101. Now, shift arithmetic right means if the most significant bit is 0, you are going to enter zeros. If the most significant bit is 1, then we are going to enter 1. So 3 ones are going to enter, and these 3 are going to exit. So my answer will be 0 1. شوف الأولانية صح؟ Yeah. 0 0 1 1 0 0 1 1 0 1 1 1 1. And this is F6. Okay, F6 as your answer. This is the difference between shift arithmetic right. So in total, shift shift right is not equal to shift arithmetic right, because in shift arithmetic right, whatever is the most significant bit, you keep entering into your program. In comparison to shift left and shift arithmetic left both are the same. Now let's rotate. In the rotate instructions, if I say move to CL, sorry, I shouldn't use CL. Move to BL 51 hexa, and then rotate right. Okay, rotate right BL 4 times. Rotate right BL 4 times. So what happens is, first you need to get the this one change. So it is 1 0 0 0 and 5 is 1 0 1 0. Then we need to rotate right. Rotate right means move the bits to the right. So I'm going to move 4 bits from here to here. So you take these 4 and you put them here. So it will be 1 0 1 0 1 0 0 1. Sorry, 0. Okay. So in rotating we can, so it is 0 1 0 0 0 0 1. So the first step, we are going to move this one over here. So we get 0 0 0 0, sorry, 0 0 0, 3 zeros, then 1 0 1 0, and this one came over here. Then we are going to move this 0 over here. This is the second step. So after this step, we are going to get 0 0 1 0 1 sorry, 0 0 1 0 1 0, then the black one and the purple 0. If we move another one, okay, then this 0 needs to go over here, and so you will get your answer as 0 1 0 1 0 1 0 1 0 1 0 0. And finally, the final step is moving this number over here to over here, so you get 1 0 1 0. Okay, so you get 1 0 1 0 0 0 0. Right answer. Okay, which is the right answer. So what we get is, can you just give me 1 second? Hello? Yeah, Raj. Just I'm in the class. Okay, sorry for that. So at the end, you get the answer as 0 1 1 0 0 1. So basically, you move. What we did is I took these 4 and moved them over here. If you want to do the steps, you can do the steps. If you want to do the shortcut, you can do the shortcut. So this is rotate right. We can do the same for rotate left. If I say move to BL C4 hexa, and this is should be add. Then rotate left BL by 3. So first of all, you need to change this into hexadecimal, into binary number. So the binary number is 0010 0011. This is 4 and this is C. So we want to rotate left. Rotate left means move the bits to the left, but by rotating. So these 3 will move from here and they will come over here. So the answer will be 0, 1, 1. So these three already moved, and the rest will come 0, 0, 0, which is 2, 6. Of course, you can do it in steps. If we want to do it in steps, it is 0, 0, 1, 0, 0, 0, 1, 1. So the first step is to move this one over here. So you get 1, 0, 0, 1, 0, 0, 0, 1. Then we move this one over here. So we get 1, 1, 0, 0, 1, 0, 0, 0. And finally, we move this 0 over here. So we get 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, which is the same answer over here. So we move these three, and we got the answer. It's the same answer that is on top over here, which is 26. As for rotating carry, you need to know what is the carry bit, and in that case, the carry bit will be included within the process, which is this part over here. If you know the carry bit, then the carry bit will be there. There was one instruction which was set carry. If the set carry instruction was used, then the carry bit is equal to 1, and then the rotation will be a little bit different. So we can do an example over here. So if I say, assume the carry bit is equal. I assumed the carry bit is equal to 1, and I said then move to AL E5, 0 E5 hexa, rotate carry right AL by 2. So basically what we are going to do is first first I'm going to change whatever is in E5, which is 5100, 1010. E is, since I'm going to rotate right, then I'm going to move my bits to the right, but now it's rotate carry, so my carry bit 1, so this flag, and it is equal to 1. It will be included in the rotation process. So the first step, this one will come over here and this one will go back. So I will have, after the first, this one you cannot do it immediately. So this one first, you take this one, put it here. So you will end up with carry flag equal to, which is this value. Okay, this one will go here and this one will go here. So carry bit will go over there. Then you will have 0, 1, 0, 0, 1, 1, 1, and this is the one that came from here. Okay, this one came from here. So the next step is to rotate one more time. So this one will go to the back and the 0 will go to the flag. So 0, then you have 1, 0, 0, 1, 0 go here, 1, 0, 0, 1, 1, then you have a 1, 1, 1, and 1. So this is F9 as your answer. So this is the whole thing when it comes to using the carry flag in your question. Okay. Anyone has any question on this part?
Doctor, I have a question for mol, the big number, how it comes. Because when I tried that to find that numbers, it doesn't come.
What do you mean by big number?
Mol, examples of mol.
Multiplication.
Yes.
You mean, what do you mean by big number?
In the examples, the result, it comes a big number like 429, 483.
Okay, okay.
I know it is by multiplication, but when I tried to get that, it doesn't come.
Did you use the
how
emulator,
no,
or you just multiply?
I used
Okay,
the
let me
calculator
show you.
program.
It was in this lecture then.
In week 13.
Yes, this one, this one. So which example you mean? You mean which number?
First example. This
This one?
yes.
Yes, and in this one, look, if we do multiplication for f multiplied by f, you are going to get this result in decimal and this result in hexadecimal. So if I do the calculator here, okay, and I will show you later on in the program. If I multiply f multiplied by f to FFFE0001 or 4294482225. Okay, of course, this is if we do a, um, a multiplication for positive numbers. If it's a negative number, this is the distribution of the bits. Okay. Okay, we don't have that option here. Now, if you want to do it on the emulator, we will have to do the following. Okay, we will have to do the following. Let's go to the emulator. In my emulator over here, I will say move to dx0, move to ax. طبعا ax will not contain more than okay, ax, move to ax 0 FFF hexa, then move to BX 0 FFFF hexa, then mul BX. Now the first instruction, this one is only used for preparing the register DX. I want to make sure that DX is empty, and this was explained in the lecture notes. We need to make sure that before doing the multiplication, لأنه part of the multiplication result will be stored into dx. Now, if we do the emulation over here, move to ax FFFF, move to bx FFFF, mul bx, it will give you the answer as FFFE 0001. Okay, FFFE 0001. Remember, it's a cascade between ax. It's a cascade between dx and ax. Now, if I do over here, instead of mul, I do imul. Over here, when we do imul, means use the numbers as positive and as signed numbers, basically. So it will be multiplying -1 by -1, and the answer will be basically 1. Okay, it's multiplying -1. FFFF is -1, but x, which is -1. -1 multiplied by -1 will give you the answer at 1. And remember, the carry flag / overflow flag, if both of them are equal to 1, this means that my answer is displayed in dx and ax together. Okay, any other questions? Any other questions?
Doctor,
Doctor,
Yes, Afifa.
these all these instructions like mul and those shift, rotate, and all those, you'll be asking like a program to write it as a program, or Like in what way?
Usually I ask what is the output. Okay, I give you instructions and I ask you what is the output, because if you understand what is the instructions doing, then you understand them. Now,
So
you need to keep in mind that there are some parts where you have to write programs, similar to what I did last time in the tutorial.
So for these parts, like you'll just ask the final result, right?
Yes, yes, yes. Look, the whole or in the university, we are trying to make sure that you don't suffer a lot when you try to solve the exam. So we will try to make the answers as short as possible. Now, fortunately for this, the instructions are too small and everything you need to type is very easy to do, let's say. So basically, you have to do it in small programs. So either you go for the final answer or you write a small program. Any other questions? Okay, if no more questions, I will be seeing you, inshallah. I will not be seeing you, inshallah. I will be seeing you, inshallah, next semester. For the exam timetable and the further details, we will be discussing with the registration department. Exams will start on 2nd of May. يعني not next week. The exams for this course will be, of course, in the evening time in the 3rd session, because we have evening students with us. So, any questions, anything before I leave?